Hey everybody, let's look at this problem here from 1988, what I would generally classify in not a helicopter problem, it is a helicopter in this one, but an elevator problem. So first part here, it says a helicopter holding a 70 kilogram package suspended from a rope 5 meters long accelerates upward at a rate of 5.2 meters per second squared. The fact that it goes upwards is important, and it's a 70 kilogram package. Neglect air resistance on the package. So first thing, do a free body diagram of all the forces on the package. Well, we know that we have the force of gravity downwards on the package, and of course, we've got a tension upwards on the package, and that tension must be larger than the force of gravity because the package is accelerating upwards, and so the up force is winning there. So let's go on to the next part. It says determine the tension in the rope. So all of these wind up being, whether it's tension or normal force, done the same way. We want to start with Newton's second law. So we say the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. So the next thing, let's think about what forces we're summing up. We've got the tension up minus the force of gravity down. And as we say sometimes in class, we don't plug in a negative for g later. I put the negative right there. That's downwards. So that will equal the mass times the acceleration in the y direction there. Next thing, let's add this force of gravity over to the other side. So we get tension is equal to force of gravity plus mass times acceleration in the y direction. And now let's write out what the force of gravity equals. The force of gravity is mass times gravity plus mass times acceleration in the y direction. And you can factor out that mass if you want, or just leave it right there. So now let's go on and plug in specific numbers from this problem. And so the tension here will equal, the mass is 70 kilograms. We multiply that by gravity here on Earth, 10 meters per second squared, and we add that to the second term, which is the mass again, 70 kilograms, and we multiply that by the acceleration in the y direction, which if you remember from the front page said it was 5.2 meters per second squared. Sometimes I think about these as this is the force to just keep the package from falling downwards. It's balancing out the pull of gravity, and this is the additional force to get it then to accelerate upwards. But they're not really two different forces, but that sort of makes it solidify in my brain. All you got to do then is the math to work this out, and you should get that it's 1,064 newtons is the tension. All right, last part here on this one is it says, when the upward velocity of the helicopter is 30 meters per second, so that is upward, right? And it's going 30 meters per second. The rope is cut and the helicopter continues to accelerate upwards at 5.2 meters per second squared. The package, however, is in free fall at this point since the rope was cut. Determine the distance between the helicopter and the package 2 seconds after the rope is cut here. Okay, so one thing to sort of keep in mind, I'll do my rough drawing of the helicopter here, is that remember, the rope was 5 meters long. So in a sense, if I call this like the starting position of the package, I'm going to say the helicopter had like a 5 meter starting lead over the package there. So I'm going to figure out the distance between the two. And in order to do that, I got to figure out how much displacement the helicopter had and how much displacement the package had. And then I'm going to add those two things up here. So let's start with the displacement that the helicopter had. And to do this, I'm going to use the third kinematic equation. So we've got the initial position of the helicopter plus the initial velocity of the helicopter times time plus 1/2 times the acceleration of the helicopter times time squared. Now let's start to plug in for all of these variables here. So the displacement of the helicopter is its initial position, as I was saying over here, is 5 meters. It had a 5 meter head start. Its initial velocity is 30 meters per second. The time we're talking about here is 2 seconds. The acceleration remains at 5.2 meters per second squared. And again, here comes our time of 2 seconds again. And let's work this out. You will get from all of this 75.4 meters. Now, let's do the package here. We're going to do the third equation again, but this time from the package's point of view. So the displacement of the package, we're going to use all of this, same equation right here, but for the package. The package started at 0 position, so the package's initial velocity was also 30 meters per second. We're talking about this same time of 2 seconds, and so the difference is when we get to the acceleration of the package, it's in free fall now. So its acceleration is negative 10 meters per second squared, and then 2 seconds again is the time. And if we work out all of this math, we get 40 meters. So the helicopter moved up 75.4 meters. The package actually moved up. It hasn't stopped moving yet. And so it moved up 40 meters yet, 40 meters vertically. And so we just got to look at the difference between those two, and we see that we get 35.4 meters is the distance between the helicopter and the package.